This is part 2 of an example problem for a single stage batch distillation. And so in the first part I went through the details of the problem statement and then the equations and then a diagram of the system here. But the equations that we're going to use are repeated here. And what I want to concentrate on here is the approach to solve these equations using a spreadsheet. Now, in order to do this integration for the Rayleigh equation in the form that we're going to put into the spreadsheet is here, we first have to know the saturation pressures from the Antoine's equation in order to calculate XW and YD, the two values in the denominator. However, we need to know the temperature to calculate the saturation pressures. Instead, what we know is the starting value for XW0. So what's done in the spreadsheet is determine the temperature. And so if we just look at this column here, and I'll explain in more detail what these are, but I set solver to vary the temperature to determine XW value of 0.82. That then was the starting temperature in the system, and then I stepped through temperature to do the integration. So let's look at the columns in the spreadsheet. Saturation pressure 1, this equation, saturation pressure 2, of course here. XW is then calculated because we know at given temperature, saturation pressure and the total pressure is fixed. YD is then calculated from this equation. So this is YD. Well, this is just calculated from the previous two columns, XW and YD. The integral, we're going to use essentially an Euler single small steps to calculate the integral. I'll talk a little more about that. But the integral, so this integral is this term here. Then W is this equation where we have the exponential times the starting value of W. D is just a mass balance. That's this equation gives us D, and then XD, the average, is here. And so what I've done is step through in temperature and pick small enough step sizes, so increase the temperature by 1/10, because as distillation proceeds, the temperature is increasing as we remove the more volatile component. So let's just talk a little more about this integral. So what we're doing, if we were to look at a plot, our variable XW, the mole fraction in the still, and we're integrating 1 over YD minus XW. So let's say the function looks something like this. We're starting at a high concentration, XW0, and essentially a small step, you can see XW decreased here for our first step. So we've decreased XW, and then we decreased again and again. And the step sizes in XW are not uniform because we're instead taking uniform step sizes in temperature to make this calculation easy. But we can calculate the area by this difference in XW between the steps, this difference here, for example, for the first one. Now we could do it times the amplitude of the curve. So if I were to blow this up, we have some value here for the next one. We could use this value. What we're going to do is take the average of these two values. So it gives us better approximation to the area. And that's all we're doing then with this integral. Stepping through, you notice it's a negative value because we're decreasing x. The y value is positive, but delta x is negative. We then calculate, with each step, we can calculate W and D, and we'll keep doing this. And I just show here a few steps. In order to have accuracy, we want to take small steps. We keep doing it until this is equal to 0.90, because that's That's our criteria for the problem statement. When that happens, then here are the values for XW, W, and D. That's what we're desired to determine. So let's briefly look at this spreadsheet. Well, here's the spreadsheet. You've seen the first part of the spreadsheet. All I want to do is scroll down. We scroll down, we see XD average is decreasing, the right-hand column. And I carried out this integration until we got to 0.90, which is what the problem asked us how much was left when the distillate was at 0.90. So you can see we have 12.46 moles left in the still, and we've distilled over 62.54 moles. Well, we can also look at these equations in a little more detail. So let's look at this formula page. So you can see I've stepped through. This is my starting temperature, and I add 1/10 of a degree. I then just use the Antoine equations for P1 sat, P2 sat. XW is the equation that results from Raoult's law, and likewise YD, Raoult's law. Then this column is just obtained from the previous two columns, H and I columns. And then here's the integral. So I take K9, previous value, well, initially there's no area, and I add the step in HW, and then I add the average of these two integral terms to get a more accurate integral. And I step through this way. To get W, I take W0, which I've defined elsewhere on the spreadsheet, their starting number of moles in the still, times the exponential of this integral term. And then I use just a mass balance to get D, and then the average. This is also from a mass balance. So spreadsheet, very efficient way to do this integration, and very quick to do the calculation.